I'm Kunal Iyer, and I'm honored to be able to present my work at the Advanced Motion Control Conference this year. I shall be presenting my work on offline and online tire model reconstruction by locally weighted projection regression in collaboration with Dr. Shyrokau from the Cognitive Robotics Department at TU Delft and Dr. Valentin Ivanov from the Automotive Engineering Group at TU Ivanov. Let us first go through some main talking points of this presentation. I shall start off with the motivation behind my research, followed by the research question. I shall then introduce some tire force reconstruction methods. I shall then briefly talk about the proposed algorithm. This shall be followed with some results and discussions on it. I shall then discuss an application of this algorithm for path following control. Finally, I shall conclude my presentation with some advantages and disadvantages of this algorithm. It is very difficult to understand what exactly is going on inside a tire at all times. So let us go through some key motivational points. Firstly, dynamic tire behavior is extremely nonlinear in nature. Secondly, we have the variation of tire properties. This may be due to variation in tire temperatures, tire pressures, or due to wear. Thirdly, a controller must hence be able to adapt to these varying tire properties online. This leads us to my research question. To ensure safety, comfort, and performance in vehicle motion control systems, the system needs accurate tire force data, especially in real time. Moving on to the tire force reconstruction methods, there are three basic methods. Firstly, we have the tire model based method, where this represents a virtual tire sensor using a fixed tire model. In order to encapsulate the entire tire behavior, complex and precise models are required. This makes it unsuitable for real-time applications. Some commonly used models are the Dugoff tire model as well as the magic formula model. As well as variations of Kalman filter can also be used as an estimator. A priori knowledge of the vehicle states is required for this type of tire force reconstruction. Moreover, some states like slip related states cannot be measured directly, and this requires extra estimators. These points lead to the conclusion that this method is increased in its complexity. Secondly, we look at tire model free methods, where the tire model is no longer required. This can further be classified into three methods. Firstly, we have vehicle dynamics based methods, where acceleration sensors and GPS signals are used, and force balance equations are used to derive the tire forces. Secondly, we have wheel rotation based methods, where the wheel speed sensors are used. Here, torque balance equations are used to derive tire forces. Thirdly, we have stochastic methods, where forces are treated as black box variables and vehicle planar models are used to reconstruct tire forces. This type of method is suitable for uncertain road friction parameters. However, its complex tuning and computational costs are a big drawback. Next, we have sensor-based methods. Sensing technology is known to be accurate and robust. We have different types of sensor-based methods. Firstly, we have suspension bushing, where eddy current displacement sensors are used. Drawback of this method is the complexity of the approach and the durability of the bushings. Secondly, we have the knuckle and brake calipers. Here, strain resistance elements are used for tire force reconstruction. However, only brake torques can be measured, and the temperature dependency of this method is a drawback. Thirdly, we have wheel force transducer, where strain measurements in the wheel rim are used for tire force reconstruction. This method, even though with high accuracy and bandwidth, it is expensive. Other methods such as load sensing bearings have also been researched upon. Apart from the discussed tire force reconstruction methods, we have a new one which is known as the hybrid method, which uses the same analytical base as a tire model free method and a sensor based method. Locally weighted projection regression, or LWPR, falls into this category. So what is LWPR? The main idea is to approximate nonlinear functions by piecewise linear models. Let us take three cases. So the dotted line shows the nonlinear variation, and the red line shows the linear approximation. As you can see, the least squares and the weighted least squares method do not provide a good approximation. However, the locally weighted least squares divides the nonlinear region into three locally linear regions, and the overall approximation is a combination of the linear approximations of these three regions. Given a query point x, the function to be learned is constructed by blending locally linear models psi in the form as shown, where wk is the locality kernel of each receptive field and f of x encapsulates the entire past dynamic information. For learning these locally linear models psi, LWPR uses locally weighted partial least squares regression. Within each of the linear models, latent variables are derived in selected directions, and the output of the local model is then formed by a linear combination of these latent variables. Let us revisit some of the motivational points discussed earlier. We know that the dynamic tire behavior is nonlinear in nature. We know that there may be variation of the tire properties due to external factors. Also, that the controller must be able to adapt to these varying tire properties. So when do we actually use LWPR? We use LWPR if the function to be learned is nonlinear, if incremental and online learning is required, and if the model requires adaptation since the target mapping changes over time. These points precisely address the three motivational points discussed earlier. How do we go about using LWPR? Again, to reiterate, the general goal is to approximate nonlinear functions. I shall go over the algorithm briefly. So we start with initializing the algorithm with 0 receptive fields. Then for each data point xy and for each receptive field, we compute an activation. The receptive field is chosen to be Gaussian in nature usually, and the weight or an activation is as shown, where ck is the center of the kth linear model and dk is the distance metric of the kth linear model. I shall revisit this point later. For each input vector x, every local linear model gives a predicted output yk, and the total output of the network is a weighted mean of this predicted output. The next step is to update the partial least squares and the distance metric. In the incremental partial least squares, we have lambda, which is a forgetting factor, which is used to determine how much of the past data needs to be forgotten. Furthermore, the PLS finds the optimal projection direction corresponding to the gradient of the assumed locally linear function to be approximated. An important part of the PLS is to choose these projections according to correlation of input-output data. The next step is the distance metric update step, where the distance metric is basically a parameter that determines the validity of the local model and hence influences the shape and size of the receptive field. The distance metric d is optimized individually for each receptive field by using an incremental gradient descent based on stochastic leave one out cross validation criterion. This is done as shown, where M is upper triangular in nature and the recursivity in M is as shown in the slides, where J is the cost function to be minimized. The next step is to check whether the computed activation is greater than a threshold or the receptive field check. So the threshold is something that determines when to create new receptive fields. The algorithm also recursively keeps track of the mean square error as a function of number of projections in a local model to determine when to stop adding projections. This is done as shown, where R is the number of projections. If this condition is true, then the whole algorithm is repeated for the next data point. If it is false, then a new receptive field is created and then the process is repeated. This is the end of the algorithm. Before we move on to the results and discussions, I would like to first address some key parameters. So we have alpha, which is an initial component-wise learning rate for gradient descent. It was noticed that larger values of alpha led to instability in convergence, however smaller values led to delayed convergence. Secondly, we have the forgetting factor, where large values imply more of the past data being forgotten. Thirdly, we have the initial distance metric for each receptive field. A large value of the initial distance metric means that the receptive fields are narrower and larger in number, which may lead to overfitting. Lastly, we have the smoothness penalty term. Large values imply smoother functions. So firstly, let us look at offline learning. As you can see, the inputs are the wheel slip angle alpha and longitudinal slip kappa, and the lateral force has been reconstructed using this algorithm. Similarly, the longitudinal force has also been reconstructed to a good degree with a low mean square error. Moving on to the online learning for the one-dimensional case, we have the only one input, which is the wheel slip angle, and the lateral force is learned. As you can see, the blue line shows a poorly initialized model and the dotted line shows the true force data from the Delft Tyre model. This true force data is being made available to the learning module over different durations of time, and its performance has been analyzed. As it can be clearly seen, the more time that the model is exposed to the true data, the better the learning performance. Moving to the two-dimensional case, this is the Hockenheim racetrack, and apart from the wheel slip angle, the normal force is also included as one of the inputs, and lateral force has been learned. Again, as you can see with the blue curve, the model has been initialized with a poor model, and the dotted line showing the true force data from the Delft Tyre model has been made available to the learning algorithm. It shows good learning performance. As you can see, the red line has completely converged. A possible application of this algorithm is in path following control in combination with MPC, or model predictive control. The setup is as shown, with a vehicle, with a learning module and the controller. The learning module receives sensor data from the vehicle, which then provides the learnt model to the prediction model within the MPC. The MPC tries to track the reference by providing an optimal control input while simultaneously obtaining vehicle state information from the vehicle. This has been applied for autonomous racing scenario, where the vehicle is exposed to multiple laps of the same circuit, which is an ideal place to test learning algorithms. As you can see, the simulations were run on the Scalexio real-time machine, and along with the IPG car maker hardware in the loop setup. The setup is as shown, where the vehicle states can be seen along with some controller data, which shows the learnt force, where the vehicle attempts to learn the tire behavior online during the race. It can also be noted that the turnaround time for the task is significantly low, validating it for real-time applications. Furthermore, it can be seen that the simulations are run for varying velocities and for varying lateral accelerations. In conclusion, I would like to say that this algorithm is immune to catastrophic forgetting, which is the tendency to forget old data when encountered with data from a different distribution. This algorithm develops a notion of experience for the controllers. Furthermore, it is, as shown before, is well suited for real-time applications. The forgetting factor within the algorithm helps it adapt to these varying properties online. However, this algorithm currently is limited in its applicability, in that it can only be applied for two inputs right now, but in further applications it makes sense to extend this to multiple inputs in order to encapsulate entire tire behavior. Also, the tuning complexity of the method is a huge drawback. I would like to thank Dr. Barris and Dr. Valentin for their support in this research. Thank you.